Since we were required to use the three types of integrated circuit, the AND, OR, and NOT, we analyzed how many gates would be needed to complete the circuit properly. So, based on the logic needed, we designed this circuit with 8 inputs and several logic gates to meet the required condition. The diagram shown includes a mix of AND, OR, and NOT gates. So we have 4 AND IC and it has 4 outputs each, so it is equals to 16. We also have 3 OR IC and it has 4 outputs each, so it is equals to 12. We have 2 NOT and it has 6 output each, so it is equals to 12. So in the diagram, the IC in the blue box is a NAND gate and the IC in the red box is NOR gate. The IC in the yellow box is the XOR gate and the IC in the green box is the XNOR gate. This results a total of 9 integrated circuits and 40 gates used in the entire circuits. These IC are essential because they allow the logic to be broken down into a simpler parts. The circuit was carefully constructed to meet the requirements using the appropriate number of ICs. It ensures that the outputs responds accurately to the 8 inputs condition, fulfilling the desired logic operation. The use of multiple logic gates and IC plays a vital role in making the circuit efficient, organized, and functional.
So let's move on how to get the Boolean expression of a logic diagram. So first thing first, we get the expressions for the column 1, which are directly connected to the inputs. These are the product of A and B, the product of C and D, the product of E and F, and the product of G and H. And for the column 2, the sum of A plus B, the sum of C plus D, the sum of E plus F, and the sum of G plus H. And for the column 3, the sum of A plus D, the product of A, B, C, D, the sum of A plus B plus C plus D, the product of E, F, G, H, and the sum of E plus F plus G plus H. And for the column 4, the complementary product of A, B, C, D, the complementary sum of A plus B plus C plus D, the complementary product of E, F, G, H, and the complementary sum of E plus F plus G plus H. And for the column 5, which contains 7 logic gates, beside them is their expression. And for the column 6, contains 6 AND gates, beside them is their expressions. And for the column 7, which contains 4 logic gates, which are 3 OR gates and 1 AND gates, beside them is their logic expression. And for the column 8, which contains only 3 logic gates, beside it is their expression. And for the column 9, which contains only 1 logic gates, beside it is their expression. And for the column 10, that contains only 1 logic gates, and beside it is their expression. And for the column 11, which is the last gates, beside it is their expressions, which also serve as the Boolean expressions of our logic circuit diagram. So these are the final Boolean expressions of our logic circuit diagram.
Hi everyone, so in this part I will be exploiting the truth table using an Excel. So here we can see that there are 8 inputs which labeled as A, B, C, D, E, F, G, and H. So each of these inputs can either be 1 or 0, which means there are 256 possible combinations in total. Now let's go how we come up with the output. So to do that, let's break down our logic step by step based on expressions. So based on the purchase diagram, the IC you can see there is using an AND gate, and it is connected to the 2 switches which are A and B. So meaning if it is AND, it is multiplication. So to come up to this result here, this one, I will show you how I did this part. So I'll go to the formulas first and then find the logical and then this and because we are looking for the AP. So since the A here is located to B, so I will put B here since the numbers or the expressions are located to the row 2. So I will put 2 here. And for B, since the B is located to C, let's put C here and then put 2 for row 2. So, okay. And then this is it. You just had to drag it downward, and then it will result to this. So meaning, if false, the translation of false is 0. The same here. Let's look for 1 so that we can tell that it is correct. There's no 1. Here there is 1. So you can see that if it is true, the translation of it is 1. So that's it. To show you how did I translate that from word to a number, you just have to put equal and then click N, open parentheses, and then click the value, which is this, and then enter, and it will translate that one. That's it. So I will just delete it so that it is not confused to see, and to confirm whether it is accurate or not, I will hide it so that you can better see it clearly. That's it. So A times B, 0 of 0 equals to 0, and if it is 0 and 1, it is also 0, 1 and 0, 0. It will just 1 if it is both 1 here, since it is multiplication. So that's it. So the same for C, D, E, F, G, H. The procedure is just the same. So moving on, let's go to the A plus B. Since the gate you see on the purchase app is OR gate, so meaning you will have to add the 2 switches, which are A plus B. So to do this, you have to click the logical again and then find the OR, since it is addition OR. So since the A is located to B and it is in row 2, so B2, and for the B it is located to C and then row 2, so C2. Then okay, and that's it. So to translate it again, you have to just put an equal, put an N, open parentheses, and then click the value, and then enter, and that's it. It will automatically translate the word into its expression. So that's it. So to compare whether it is true, I will show you. I will hide it to show you. So 0, 0, 0. If it has 1, it will result to 1 like this. And if it is both 1, it will also result to 1. So the same goes to A, B, C plus D, E plus F, G plus H. The procedure is also the same. So moving on here for A, B, C, D, I will show you how I did this also. So click the logical since it is and with 4 switches, we just have to locate where the switches belong to. Since A is located to B, so B2, the same with B, it is located to C, and then row 2, that's it, same procedure, and then okay, and it will result like this. So you just have to translate it again. So these are the translations I have made. I will not do this again because I already showed it earlier. So to make it sure if it is accurate, I will show you. So 0, 0, 0, 0, it is 0, and it will just show 1 if all inputs are 1 since it is multiplication or AND gate like this. So for AB plus CD, that's it. I just use in the logical the same earlier, which I used the OR, this one, and these are the results for this. So 0, 0, 0, 0, since it is OR gate, if it has 1, automatically the result will be 1. So the same with EFGH. The procedure is also the same as what I did earlier. This one, AB plus CD is the same with this. So the procedure is also the same. And for not like this, we just have to automatically click the nut here on the logical, this nut, and since this is located to W, you will put here W row 2, and this is it. So since the result here is 0, it will just invert here. That's why it is true, because the other one here is 0. So just like this here. The same goes with here A, B, C, D. I just used the not in the logical and based the letter here since it is located to S and row 2. The same goes with here, like this. Just use the not on the logical. The same goes with the procedure I did earlier. This is what we have come up for the result. And that's all of it for the truth table. I hope you learned the techniques I have shown, so that if you do a truth table, it is easier and not that much hassle for us.
Now in this part, I'll be simplifying a complex Boolean expression from our logic circuit diagram using a fundamental Boolean algebra laws. Our goal is to simplify the given expression to make it easier to understand and implement in digital circuit. So let's begin. So this is our Boolean expression from our logic circuit diagram. Q equals A plus B plus A B C D naught times A B C D naught times A plus B plus C plus D naught times C D naught plus C naught D plus E F naught plus E naught F naught G H naught plus G naught H times A F G H naught times E plus F plus G plus H naught. Okay. Before we simplify, I decided to divide it into three terms so that at least we could reduce its complexity. As you can see here, A plus B is our red term, and this term is our yellow group, and this one is our blue group. Okay, let's start to simplify. Since the red term A plus B is already simplified, we will now move to the first term of the yellow group, which is the ABCD naught times ABCD naught. The first step we will do is we apply the idempotent law, which tells us that the repeating value, same value rather, with and doesn't change the result. So since this is our repeating value with and, ABCD naught times ABCD naught is just equals to ABCD naught. Now this is our updated expression with our simplified term here in from the yellow group. Um, Next, we apply the De Morgan's theorem to this part of the expression. De Morgan's second law states that the complement of a sum becomes the product of the complements. So this A plus B plus C plus D naught will now become A naught B naught times C naught D naught. Therefore, this will be now our updated term. Next, we still apply the Morgan's theorem, first law to the next expression. First law states that the complement of product becomes the sum of the complements. So, therefore, this expression C D naught plus C naught D naught becomes C naught plus D times C plus D naught. And if we simplify this expression, this will also become C naught D naught. Now this will be our updated term. Now let's move on to the blue term, which is the here. The blue. This is our blue term. But for now, let's first simplify the first term, which is the AF naught plus E naught if naught. And then again, we will apply the De Morgan's theorem. So, this term AF naught plus E naught F naught will now become just like the what we did earlier. It will now become E naught plus F times E plus E flat. Okay. Now, the term, as you can see here, the term GH naught plus G naught H and AFGH is already in simplified form, so we leave it as it is and jump to the last term, which is the A plus F plus G plus H naught. And still we will apply the De Morgan's theorem. So this term now becomes A naught F naught times G naught H naught. So this is our updated term. After we did a simplification on each term, we will now simplify the uh, yellow group here. So let's simplify this, the yellow group. When we multiply this whole yellow term, yellow group rather, only the common part remains. So as we all know, ABCD not, since there's a parenthesis here, this is also A not, B not, C not, D not. So if we multiply this whole term, the common part remains, which is only the A not, B not, C not, D not. Or we can write also it like here. And now it's time for the blue term to simplify. As you can see here, in blue term, when we multiply the entire group, especially the this one, J H naught plus G naught H times G naught H naught, it simplifies to 0 because these expressions contradict each other. So this entire blue group becomes 0 and does not affect the outputs. So now we're left with this simplified Boolean expression. Q equals A plus B plus A, B, C, D naught. So this is our final simplified expression. Q equals as A plus B plus A, B, C, D naught. Now let's verify if our simplified Boolean expression has the same output from our original Boolean expression. So let's open the our, what do you call this, Excel. As you can see here, I already wrote um yeah, our simplified Boolean expression. So we'll just write to know the output on each combination. We'll just use formula, because there's a lot of possible combination. That's why it's better to use formula. Pause. What's it? Or. Since this is plus, we're using or. And then we'll find A plus B and A, B, C, D not. Maybe A plus B here, A plus B. So we'll write 0 to equals 1, 0 to equals 1. And then x2, since we are in column x and row 2, plus 1 times what? So this is our the output. We'll just drag down here. Mm. So as you can see here, our simplified expression and our original expression, Boolean expression rather, have the same output. So that means our simplified expression is correct. Okay, let's verify if it has the same output here. There's the 1 here, then 0. So we just verify its output if the original and our simplified expression have the same output, and as you can see, it has a same output. So that's all. Thank you.
This will be the final stage of our project. which is the building of the circuit and the digital trainer based on the logic diagram we designed in Proteus. So the components used are the 4 AND gates, which is the IC74LS08, 1, 2, 3, and 4. Then the 3 NOT gates, which is the IC74LS32, 1, 2, and 3, and the 2 NOT gates, which is the IC74LS04, then 1 and 2. So we have a total of 9 IC. So by combining these gates, we've constructed NAND, NOR, XOR, XNOR, and XNOR gate to achieve the desired logic function. So in the wiring setup, we use the color-coded wires, yellow for the 8 input, black for the ground, red for the VCC, assorted colors in the connections between the gates, logic gates, and the white for the output. So now I'll demonstrate the circuit's functionality by testing the 10 different input combinations and showing their corresponding output on the digital trainer. So first is the 0 0 0 0 0 0 0, which has high output, 0 0 0 0 0 0 0 1, which has high output, 0 0 0 0 0 1 0 0, which has high output, 0 0 0 0 0 1 1 1, which has high output, 0 0 0 1 0 0 1 1 0 0, which has high output, 1 1 0 0 1 0 0 1, which has high output, then 1 1 0 0 1 1 0 0, which has high output, then 1 1 0 0 1 1 0 1, which has high output, then 1 1 0 0 1 1 1 0, which has high output, and lastly 1 1 0 0 1 1 1 1, we have high output. So through the hands-on implementation, we've successfully translated our Proteus logic design into fully functional circuit on the digital trainer. So this precise arrangement of AND, OR, and NOT gates combined into NAND, NOR, XOR, or AND XNOR configurations validates our theoretical approach. By testing 10 input combinations, we confirm consistent high outputs, proving the circuit's reliability. So this exercise not only reinforced our understanding of digital logic fundamentals, but also highlighted the importance of organized wiring and methodical testing. So mission accomplished.